So I'm going to talk about difference equations, an introduction to difference equation. This is section 11.1. A difference equation is a pair of equations. It's not a system, but it's just a pair of equations. And we use them to generate a sequence of numbers. The terms of the sequence, we usually use y and little subscripts to tell which term we have. We have y0, y1, y2, y3, y4, and so on. It goes on indefinitely, so it's an infinite sequence. And let's take a look at an example of a difference equation. y0 equals 2 and yn is equal to 0.5 yn minus 1 plus 5. The first equation is the initial term. That gets the sequence started. And the next equation is a rule to generate the next term. And we usually group them with a bracket like that, the same way we do with the system. Okay, so let me go ahead and start looking at the first few terms of this sequence. We have y0, that's given as 2. y1, I'm going to use the rule here. y1 is 0.5 y0, that's the term that comes before it, plus 5. And in this case, y0 is 2. So half of 2 is 1. 1 plus 5 is 6. There's my y1. y2 is 0.5 times y1, the term that comes before it, plus 5. So that's 0.5. We found y1 to be 6. Plus 5. I get 3 and 5, that's 8. So each time the term comes from the one before it, multiplying by a half, there's the term before it, y2, and then add 5. So that's 4 and 5, which is 9. And I'll do another few terms just to keep this rolling. 0.5 times now the term that comes before it is y3. Found that to be 9. So that's 4.5 plus 5. And that's 9.5. And y5 is going to take y4, multiply by a half, and then add 5. So I end up here with 9.75. So the first few terms of this sequence are 2, 6, 8, 9, 9.5, 9.75, and they go on like that. We want to generate some terms here to see what's happening with this sequence, specifically whether it's increasing or decreasing or neither. And what kind of values are we getting? Is it increasing very fast or slow? And we're interested in the long-term behavior of this. I can make a graph of the terms of this sequence, and it would look like this. What I'll use for the terms of the sequence is just dots. So the first term, this would be over 0, is 2. The next one is y1, and that's 6. So that's up here. The next one is 8. So that's here. y3 is 9. That would be about here. y4 is 9.5. That puts that about there. y5 is 9.75. So we see the general shape of this graph. It's curved. You can see it kind of takes on a shape like that. But the graph is just dots. There is nothing that's going on in between those dots. In any case, we see that it's increasing. It started out to be increasing faster in the beginning, and now it's kind of slowing down. But the graph gives us an idea of what's happening with the terms of this sequence. So two questions that come up immediately. How can we find terms yn for large values of n, like y100 or y1000? How can we find these terms in a more efficient way than generating all of those that come before it and keep, getting y1, then 2, then 3, then 4, all the way up to 100? It's just way too much work. We want to know if we can jump right out to y100 and see if we can just calculate that, or y1000 or whatever. And that, of course, is the same thing as asking what is the long-term behavior of this sequence of these numbers. Here's another example. y0 equals 8 and yn equals 5, yn minus 1 minus 32. Okay, so there's the difference equation. And now I'm going to start generating some terms. So y0, of course, is 8. That's given. y1 looks back at the term that comes before it, which is y0, and multiplies by 5. So I'm going to take 5 times 8 and subtract 32. So 5 times 8 is 40, minus 32, and I get 8. And y2, I multiply the term that comes before it by 5, and that term y1 is 8. Subtract 32. That's 40 minus 32. Again, I get 8. And what happens here is pretty clear, that every time I multiply by 5 and subtract 32, I'm going to get 8. So every term in the sequence is going to be 8. 8, 8, 8, and so on. It keeps going. This is called a constant sequence. It's not increasing, it's not decreasing, it just stays the same. And the graph, not all that interesting, but 2, 4, 6, 8, let's say we go up here. 8 is the first term, 8's the next term, 8's the next term. So we just get this type of graph here. Every term is 8, and that's what it's a flat graph. We can guess what the long-term behavior on this one is. It stays at 8. It doesn't matter if it's y200 or y1,000,000, it's going to be 8. Okay, so the next example is going to be different from the first two. The first example was increasing sequence, second one constant, and we'll take a look at what happens to this one. We have y0 equals a half, and yn is -2 times yn minus 1. -2 times the term that comes before it. So let's generate a few terms of this sequence. y0 is a half, that's given. y1 takes the term and multiplies by -2, and we end up with -1. y2 multiplies -2 times the term that comes before it, which is y1, and that's a -1. So I end up with +2. y3 is negative 2 times the term y2 is 2. So this is negative 4. y4 is negative 2 times negative 4. That's y3. I get 8. y5 is negative 2 times 8, which is negative 16. So there are the first terms of the sequence, 1/2, negative 1, positive 2, negative 4, positive 8, negative 16, and so on. This is an alternating sequence because it's positive then negative, then positive then negative. And let's take a look at what the graph would look like for this. This graph is going to be a little more interesting, and I'll draw it here. First get the scale. I have 4, 8, 12, 16, negative 4, negative 8, negative 12, negative 16. So my first term, y0, is at 1/2. That's going to be close to the axis like that. The next one, which is y1, is negative 1. The next one, y2, is up at 2. And put these in here. y3 is negative 4. y4 is 8. y5 is negative 16. So what we see here are kind of two different things happening. There's this shape up here which is curving up, and this one which is curving down. The dots are alternating. This does both. It increases and decreases. Half of it increases, half of it decreases. So this is the alternating or oscillating sequence. Okay, in general, a difference equation looks like this. I have y0, some initial term, and I have yn is equal to some constant times yn minus 1, the term that comes before it, plus b. This would be the general form of a difference equation. Now if you look back at this example that we just did, I would have y0 equals 1/2. A here is negative 2. That's the multiplier of yn minus 1. But since I'm not adding anything on to that, I get b equals 0. So I can still look at this as the general form. Back up here, with this constant sequence, I have y0 is 8. That's the initial term. And a, the multiplier, is 5. And b is negative 32. So every difference equation I can write like this with a and b. And to solve a difference equation, means to find a formula for yn, any value of n, that involves only the value of a, b, and n. So we can jump out and find terms without generating the whole sequence and all the terms that come before yn for any particular value of n. For the difference equation, y0, yn equals a, yn minus 1 plus b. That's the general form. The solution is yn equal to b over 1 minus a plus y0 minus b over 1 minus a times a to the n. And let me put a note in here. This is only for a not equal to 1. We'll have to talk about what happens when a is equal to 1, because you can see I'm putting in the denominator 1 minus a, and we can't make that 0. But we'll address that later. Anyway, this is the formula for the solution of the difference equation, and it involves n, the term that I'm trying to find. It could be 100 or 1,000,000. I want to find that term. It involves a and b, which are from the general form here, and y0, my starting point. So let's take a look at the first example that we looked at. y0 is 2, yn equals 0.5, yn minus 1 plus 5, and we'll see how to find the solution for this difference equation and use it to find yn for large N. So let me jot down those terms from the previous calculations. We had these terms. Okay. The solution we're going to do in a few steps. First of all, step 1, I want to calculate this value b over 1 minus a, and you can see it occurs in two places in this formula. So in my example, we have b is 5 right here, and a, the multiplier, is 0.5. So I'll put those into their places here. b over 1 minus a is 5 over 1 minus 0.5, that's 1 minus a half, which is also a half, and I end up with 10. Okay, so b over 1 minus a is 10. Step 2 is to put them in their proper places and to put in y0. yn is equal to b over 1 minus a, that's 10. y0 is 2, so I put that in here in parentheses, minus b over 1 minus a, that's 10 again. A is 0.5, and that's raised to the n. So this gives me a formula where I can just put n right here and calculate yn. And these other numbers just stay the same. So let me simplify this. The only thing that I can do is inside the parentheses, 2 minus 10, that's a negative 8. Don't be tempted to multiply by that 0.5 because that has an exponent on it. So you can't do anything until you put a value of n in there. So let's evaluate this just for the record to show that it works. Let's say for n equals 3. I already know what y3 is. This is y0, y1, y2, y3. I should calculate 9 from this, but y3 is 10 plus negative 8, 0.5, and the 3 goes in right there. So if you get out your calculators, what you want to do is to go over here to the 0.5 and raise it to the third power. That's the first thing that you do. 0.5, raise it to the 3. You can press enter and then multiply by negative 8. And after you have that on your display, add 10. So I end up with 0.5 raised to the third power, that's 0.125. And multiply negative 8 times 0.125, that's a negative 1. and I end up with 9, which is what I ended up with when I just generated these terms one by one. So the formula works for n equals 3, and if I put any of these other terms, the value of 4, I should get 9.5, and for n equals 5, I should get 9.75. But let's see how to jump out to the 10th term and look at n equals 10. I'm going to calculate y10 with the same formula here. It's going to be 10 plus negative 8.5, but now the exponent is going to be a 10. On your calculator, go over here first, put 0.5 and raise it to the 10. That's going to be a very small number, but leave it sitting there on the display. Multiply by negative 8, get that on your display, and then add 10. And I end up with 9.992. So we noticed already that these terms are increasing, and it looks to be like they're still increasing from 9.75, that was y5. This number is a little bit bigger, 9.992, y10, and y20 should be even a little bit bigger than that. But something else is happening here, that I'm noticing these terms look to be getting closer and closer to the number 10. Of course, we're going to be interested in, does it ever reach 10? Does it just keep getting, creeping closer and closer? Does it ever reach 10 and exceed 10 because it continues to increase? And that would be the long-term behavior that we're interested in. And we'll see in the next class how we determine what happens in the long term.